Okay, today we're happy to have Hazel Mak from Brown University to tell us about the n equals 4 supersymmetric SYK model. Please.
Thank you for the introduction. I'm very happy to give this talk at Stanford. This work is done with Jim Gates, who is my supervisor, and he's also here today. And also with my fellow colleague, Yang Hu. So it's about construction of 1D n equals 4 supersymmetric SYK-Type vertices. So I'll tell you more about it today. I will start with introductions of SYK model and also supersymmetric SYK models. Then I will talk about our approach. We'll start from 4D n equals 1 like supermultiplets, and then we'll construct some of these models and project it to 1D n equals 4. So I will review some of these 4D supermultiplets and then talk about our construction process. And then finally, I will comment on the features of our models. So let me start the introduction of 1D SYK models. So SYK stands for Sachdev, Ye, and Kitev. So this model was first proposed by Sachdev and Ye to describe a random quantum Heisenberg magnet in 1993. And then in 2015, in two of the lectures, Kitev presented in the present form that we commonly use and talk about some implications of these models and their relation with holography. So it attracts a lot of interest, and there are a lot of studies since then. So this is the definition of SYK model. So we have random 4-point interactions of marijuana fermions in 1D. So these fermions are functions of times only. And this coupling J is Gaussian random with zero mean and the variance specified by a constant. So and this is a more general form of it. So instead of 4 marijuana fermions, you can have like any number of even numbers of marijuana fermions. So there are a lot of studies of SYK because of several interesting properties that it has. First of all, if you look at the IR limit with the low energy limit, and if you consider large n, which means you have a lot of marijuana fermions, it is exactly solvable, meaning like all these diagrams are dominated by Melonic-Feynman diagrams, and you can actually sum all of them to all of those. So it's exactly solvable, and it's also maximally chaotic at the same time, which is unusual. And also it will have emergent conformal symmetry in IR, and at the same time, we will have a time reparametrization symmetry, which will generate some divergences, and you don't want that. So you will break it by introducing a Gaussian mode. But then when you do this, then you realize in ADS2, like in 2D, JT dilettone gravity also is also described by Gaussian. So this suggests possible holographic duality between SYK models like the near conformal field theory in 1D and also this gravity at 2D, ADS2. So it becomes very interesting to study them. And there, like since the introduction of SYK models, there are actually a lot of generalizations of SYK. Like for example, you can like throw in some global symmetries like U1 or like some SO symmetries, or you can introduce additional flavors. There is a version of tensor model without crunch disorder, which is done by Gural and Witten and some other people. And there is also a supersymmetric version of that. It's done by Peng, Spreading, and Volovich in 2017 at Brown. Or you can actually go to higher dimensions like 2D, and there are also a study of 2D supersymmetric SYK. But today our focus will be on 1D supersymmetric SYK models. That was okay. Let me go. So for 1D supersymmetric SYK models, you can actually throw in like n equals 1 supersymmetry, n equals 2, or n equals 4 supersymmetries. The first paper that comes out for 1D supersymmetric SYK model is actually the n equals 4 one. It's by Aninos, and Denef in 2016. And then a few months later, the famous paper by Fu, Gato, Medicena, and Sachdev come out. Then they provide supersymmetric SYK models with n equals 1 and n equals 2 supersymmetries. And there are some more other references that I put here. They also discuss these models. So let me provide some review of these supersymmetric SYK models. So for n equals 1 SYK models, you can consider marijuana fermions and n of them, which satisfy this anti-commutation relation. And then you can write down the supercharge in a few theoretic representation. So there is a Gaussian random coupling that's contract with 3 of these marijuana fermions. And this is totally antisymmetric because these are fermions, and then it's Gaussian random with 0 mean and also variance specified by a constant. Then you can construct the Hamiltonian by the square of supercharge, and then you will get a term that looks like this. And this is onshore. So this is the ground state energy, but then this coupling will be written in terms of 2 of these C's, which is a constant from the supercharge. But one of the indexes are contracted, so that you can think of it as a multiplication kind of. And note that now this J is no longer Gaussian random, but this C is taken to be Gaussian random. And these people at, for example, Leo at Caltech, and also Hunter Jones, and also some of these people are from Parameter Institute. They mentioned that if you have from random matrix theory, if you have a Gaussian random matrix, which means that all the entries are Gaussian, and then if you can construct a Wishart matrix, which is a Gaussian matrix multiplied by the Hermitian of the Gaussian matrix, and that will be a Wishart matrix, and this Wishart matrix will follow the Wishart-Laguerre random distribution. So now here is something look like that. So this C is Gaussian random. So this J is actually Wishart-Laguerre random. So this is formulated like by as described by the paper by Fu, Gato, Medicena, and Sachdev. This is formally the only difference between supersymmetric SYK models and ordinary SYK models, is that distribution of this coupling is different. So so far you
sorry, I have a naive question. Sorry to interrupt. So in the previous model, could I have just forgotten about the Q and just work with the Hamiltonian and specify the J to be this Wishart-Laguerre? Would that be the equivalent model?
Yeah, you can do that.
Okay, I see. So I didn't need to know about the Q at all, basically.
Right, but we introduced this supercharge thing to introduce some supersymmetry, because if you just look at these two sides, you don't see any bosons appearing here at all. But we can actually introduce auxiliary bosons and then construct an offshore Lagrangian, which when you go onshore, and then when you like just throw out the kinetic terms, you will get this Hamiltonian. So yeah, so supersymmetry is just a more natural way to construct a model that will have this coupling that follows Wishart-Laguerre random distribution. Right.
Okay, thank you.
No problem. So now let's introduce some supersymmetry by introducing an auxiliary boson. So this is a kinetic term for propagating fermion, and this is a kinetic term for auxiliary boson. And this is the interaction term. So if you integrate out the auxiliary boson, then you can see this B will equal to this Syk Syk Syk. So you can plug that in, and then you will get this onshore Hamiltonian term. So this is the offshore Lagrangian, and then you can introduce a supercovariant derivative and also a superfield that envelops these component fields. And then we can rewrite it in a superfield formalism. So this is the superfield Lagrangian. This is a kinetic term, and this is the offshore. Oh, this is the superfield Lagrangian term. And now this Syk appears naturally here as a coupling between these three superfields. And this is Gaussian random. And you can do a version with like 4 Majorana fermions, like interaction onshore, but you can also do it like we call it 2q minus 1 point, which is a q point superfield interaction. And when you go to offshore and go to components and onshore, then you will have 2q minus 1 point of fermionic interactions. So this is the offshore Lagrangian, and now this is a coupling constant that we take it as Gaussian random, and its variance is constant. And the superfield Lagrangian looks like this. So this is a review of the n=1 supersymmetric SYK models. But we can also like throw in some more supersymmetries and do an n=2 version. So for n=2, let's consider complex fermions which satisfy these kind of like anti-commutation relations. And we can write down 2 supercharges, Q and Q bar. And these are complex, antisymmetric, and Gaussian random. And now you can write down the Hamiltonian as a anti-commutator between Q and Q bar, and then this will be the SYK term. And this coupling constant now follows this distribution. So previously I mentioned that Wishart matrix is like a Gaussian matrix, and then multiply with its Hermitian. So now these are complex. So you can see that if these two are complex conjugates of each other, so and one of the indexes are contracted. So this is a Wishart-Laguerre random distribution. And again, we can introduce some auxiliary bosons, B and B bar, and then write down an offshore Lagrangian that looks like this. And then we can introduce some supercovariant derivative operators. And also we can introduce some superfields, but now we are focusing on using chiral superfields. So we can throw this chiral superfields in and write down a superfield Lagrangian. This Lagrangian is actually given in Bollicher's 2018 paper. It wasn't there in Maldaceno's paper. So this superfield Lagrangian can be written by some like chiral and anti-chiral superfield terms. And we can have a general version of it, like 2q minus 1 point. With the coupling still be Gaussian. And this is the most general like superfield Lagrangian for n=2 supersymmetric SYK models. And we can actually like look at this term and see, because this is anti-chiral, so the acting on it will be 0. So we can actually throw this thing in front, and in superspace, like integration and differentiation are the same. So you can rewrite it in a form that's sort of like scalar potential, but now these are fermionic superfields in chiral superfields instead of bosonic chiral superfields. So the kinetic terms look like scalar potential, And also the interaction terms, because all of these are chiral and it's only integrate over the chiral half of the superspace. So it looks like superpotential. So this is the form of the superfield Lagrangian for n equals 2 supersymmetric SYK. So before I jump into our constructions, I also want to mention that in literature there is a paper that construct n equals 4 supersymmetric SYK models also. And I think it is the first paper that actually have any supersymmetric SYK models in it. So this paper is done by Aninos and Denef in 2016. What they did is they start with a chiral supermultiplet with a dynamical boson, a fermion, and also auxiliary boson. And they have some index indicating brane interactions. So this is the superfield Lagrangian. Here it looks like these are component fields, but then it integrates over superspace. But what they mean is you have a superfield, and then when you go to the lowest component, it will be this component. So it's actually a free superfield sitting here. And then this omega is the analog of the CIJK. So this one is Gaussian random. So it's written in a superpotential. All of these are chiral superfields, and then you just integrate over the chiral half of the superspace. So this is the components Lagrangian. These are the kinetic terms, and these two terms are the interaction terms that they have. That is offshore components interactions, but that will give you SYK type vertices when you go onshore. So I've talked a lot about I've revealed a lot about supersymmetric SYK models in literature, but I just want to mention a few words on why we are interested in supersymmetric SYK. So there are several reasons. The first one is the distribution of the coupling is different, because like an intuitive way of thinking about it is the Hamiltonian in n equals 1 case, for example, the Hamiltonian is the supercharge square. So and the distribution in the supercharged C is Gaussian random. So it looks like now you have a Gaussian random distribution, and then you square it, so you kind of fold the eigenvalue distribution. So all of the eigenvalues become non-negative. So this is the SYK coupling distribution, which is Gaussian, and the eigenvalue distribution is Wigner's semicircle. But for supersymmetric SYK n equals 1 and n equals 2, the coupling is Wishart-Laguerre random. So the eigenvalue becomes an distribution called Marchenko-Pruster eigenvalue distribution, but it would be all non-negative.
Sorry,
sure.
Sorry, quick question. The Wigner's semicircle is not exact for SYK, right? Maybe for Q equals 2 or something, it's true, but it's not really.
Yeah, it's
like,
well, it's a discrete distribution, so it's kind of like how to say it's discrete, so it looks like Wigner's semicircle when you go to large n. But if your n is small, then there is some deviation, I guess. Yeah, so it's talking about large n limits and right.
Okay, I thought like at least the density of states is not like has this universality, but okay, maybe.
Yeah, I think there are some subtleties. Yeah.
Okay, thanks.
No problem. So yeah, but this will be the references to look at for this discussion, and I can send you the references later. So yeah, this is the first reason that people study supersymmetric SYK. And the second reason is this n equals 1 and n equals 2 as supersymmetric SYK models are actually still maximally chaotic. The reason that I highlight it is because you can actually do supersymmetric SYK models in 2D. For example, there is a paper by Jeff Morgan, Douglas Stanford, and Edward Witten. And they did 2D supersymmetric SYK models. But then those models, like when it's in 2D, is not maximally chaotic. So I think it's a fraction of like 0.68 or something. The Lipmanov exponent. But then the 1D n equals 1 and n equals 2 models are maximally chaotic. So it's very interesting to study. So it's preserved the features of ordinary SYK models. And also a third reason is this 1D n equals 1 and n equals 2 models actually refers to superstructures in RL. So you can think about it supersymmetric 3D gravity with these models. So this is why people are interested in these models. So I will talk about our goal and method. Our goal is to construct more 1D n equals 4 supersymmetric SYK-Type vertices. And let me make a disclaimer. So like what we did is reconstruct all the, it's not all, but like reconstruct all the vertices that we can think of that will produce SYK type interactions, and it has with n equals 4 supersymmetries. But we haven't actually go to any correlated calculations. So this is just a very preliminary results. So let me talk about our method. Our method is like we'll first start from 4D n equals 1. And from there we will use some well-known like linear representations of these superfields and construct superfield Lagrangian. This is our first step. Then our second step is we'll go to components, and then we'll go to onshore to demonstrate the existence of 4 points or 2q minus 1 point SYK times. And then the first step is after we know that these are SYK type models, then our first step is to project from 4D n equals 1 to 1D n equals 4. So let me review 4D n equals 1 supermultiplets. So before that, let me introduce this chiral projection operator. We are using marijuana basis, so like these spinor indexes goes from 1 to 4. And this is a chiral projector, so you can add on the supercovariant derivative. And we say a superfield is covariantly chiral when it satisfies this constraint, and it's antichiral when we satisfy this constraint. And we can also claim like this superfield is complex linear when it satisfies this quadratic constraint. So
sorry, what is capital C?
Oh, this is the spinor metric. Yeah. So these are, we are in 4D, so maybe sorry, I should have defined this. So this is the spinor metric, and this is the gamma 5 matrix like construct by like you have a Dirac matrix like gamma 0 to gamma 3.
Yeah, I understand the gamma 5, but
yeah.
I don't know what is it,
This
like
is
the spin?
Spinor metric. So yeah, it's a
may I
so
may I interject here, Hazel?
Mm-hmm.
So I don't know if you use 2 component spinners. You have experience with 2 component spinners?
Yeah.
No. Okay. And then you know that you can contract them with the epsilon symbol?
Yeah, yeah.
This is the analog of that for 4 component spinners.
Oh, okay. I see. So it's some like bilinear invariant of the.
That's correct.
Okay. All right, thank you.
Thank you, Jim, for that
No,
explanation.
no problem. Thank you. Sorry to interrupt.
Oh, that's fine. That's totally fine. Yeah, so this is just some conventions that we use. And yeah, and then we can do some superspace integrals. Like for example, you can integrate over the whole superspace, which means in our notation with this normalization is this one. And then we can integrate over half of the superspace, something like that. So so I'll first introduce our like in our constructions we have 3 supermultiplets that we use, the chiral, the factor, and the tensor. So this is a chiral supermultiplet which contains a propagating scalar and a propagating marijuana spinor. And then you also have auxiliary scalar. And this complex scalar is satisfy the chiral condition, which means like when you write down a superfield with the lowest component, that is this scalar, then that superfield will satisfy the chiral condition. And then you can write down a component Lagrangian, which is the kinetic terms, which is the free theory. And in superfield, it can be written like this. This is the Kähler potential. Yeah, Kähler potential. And it's integrated over the whole superspace. So this is the kinetic term for the chiral supermultiplet. And we can also look at the factor supermultiplets. The factor supermultiplets contains a propagating factor, which is a gauge field. So it only has 3 degrees of freedom. And you will have a marijuana spinor. And you will also have an auxiliary scalar. So if we define the field strength, then we can write the components Lagrangian in this form. And we can do a calculation and see that if we construct a chiral current using two marijuana spinor from this factor supermultiplet and also 1 projection matrix, then this thing is actually chiral, meaning it's vanished under the action of this operator. So you can write you can construct a superpotential from this thing, and when you integrate over the chiral half of the superspace, this is supersymmetrically invariant, and this will give you the kinetic term. So this is the kinetic term for the factor supermultiplet. And the third thing is you can write down a tensor supermultiplet, which is also called a 2-form multiplet. And all of the component fields here are propagating. It has a scalar and has a antisymmetric rank 2 tensor, and it has a marijuana spinor. So again, you can write down a component Lagrangian and also a superfield Lagrangian. And this is in terms of superfield, is a real linear superfield.
Sorry, can I ask a quick question?
Sure.
If you go back to the chiral multiplet, am I misremembering 40 n equals 1? I thought the fermions are supposed to be Weyl fermions, but it seems like you managed to get them to be Majorana. Did you like impose some additional constraint or something?
Well, maybe I haven't specified, but we are in 4 components notation. So actually, like, so for example, yeah, this A will run from 1 to 4, but if you recast it in 2 component notation, let's say, then you will have alpha, which runs from 1 to 2, and alpha dots 1 to 2.
Yeah.
And then those Weyl spinors. You can split it into two of these. Yeah.
Yeah.
No problem.
Thanks.
Yeah, so we are in 4 component notation. Sorry, I should have clarified that earlier. Yeah. So then we can construct this 1D n equals 4 SYK models. So this is a slide to recall our method. Like now we have all these 4D n equals 1 superfield flying around, and we can begin to use them to construct interaction terms in superfield. And then we can check all those if they are SYK models or not, and then we can project them. And before we jump into that, let me also introduce some of the index conventions that we have. This is a marijuana spinner index that runs from 1 to 4 for 4D. But then we also have some other indexes that we label the number of copies of this chiral factor or tensor supermultiplets, because each of them just contain one fermion, but then we are constructing SYK, so we need like n of them, and n is large. So this is the index that we use to label them. And in literature, for example, in Fugato, Medicinas, and such death paper, they use that I to indicate I run from 1 to n to indicate the number of copies for n equals 1 and n equals 2. But here we will, like, after I show you all these models, we'll see that this index pair, this number of copies, and then pair with a spinner index will be the analog of this I. So that's why we didn't just call this I, but I'll mention that when I construct all these models. And then I have a brief elaboration on our step 3, which is a projection from 4D n equals 1 to 1D n equals 4. So this projection process is established by Michael Fox and Jim Gates in 2004. So how to do this projection is like in 4D, you will have field variables that are functions of space and time, which is like, for example, t, x, y, z. And then what you do is just take that field variable and then set it to be function of time only. So you just take it to be functions of time only. So when you do some other spatial derivatives on it, it will be 0. So this is how to project from 4D to 1D. So and then other indexes will remain, like if, for example, after the projection, we will see some of this mu and nu index or this spin index, but they will have different meanings in 1D. So and these are a summary of all the interaction vertices we construct. We construct it from 3 different methods, and I will talk about each of them like briefly. So the first thing we did is we construct 4-point onshore SYK from 3-point superfield Lagrangians, and this one is done entirely by chiral superfield. This model we call it CS plus 3-point. So first of all, just this is the superfield Lagrangian that we write down. The first term is the kinetic term, and the second term is a interaction term, and these are superfields. These are anti-chiral superfields, and these are chiral superfields. And this is contracted, and all these number of copies indexes are contracted by this arbitrary constant coupler, which later we can choose it to be Gaussian random. And since it's constructed entirely in superfield language, it's automatically supersymmetric. So we can go to components, and then we can go to onshore, and after we do all of those, we just pick out the term that contains the SYK term, which looks like this. So it has 4 marijuana fermions interactions, but then it has a nonlinear term in front. So we can actually define this to be an object and then expand it. And then you'll see that the first term will be will not contain any bosons, and then the second term will be other one in this bosons. So if we just take the first term, it will be the SYK term because it will be purely fermionic interactions, like just 4 of them. And the second term we will expect will be some kind of Yukawa like terms, which is like 1 boson with 4 fermions and 2 bosons with 4 fermions, etc. So this
Oh,
term
sorry,
is,
Hazel. On the
Yep.
previous slide, could I ask a question?
Mhm.
I didn't quite catch how you got the first equation on this. Did it come from the previous slide somehow, or?
Yes. So I skip a ton of steps, but
Okay,
what we
but
did is
just
first of all, this is an integration over the whole superspace. So it contains 4 supercovariant derivatives in it. And what we did is distribute all these 4 supercovariant derivatives into these fields, these superfields. And then by the transformation laws for chiral supermultiplets, we can write down each of these terms with some gamma matrix flying around. And after that, then we will have an offshore components Lagrangian. And then like for the offshore Lagrangian, then we can look at all the fields that are, all the components that are auxiliary fields.
I see. So
And
you're integrating out the auxiliary field from
we integrate out, and then in the process of integrating out the auxiliary fields, we generate some nonlinear terms like that.
And I see. And
But
the
the
new
offshore,
thing,
the
new thing in the previous slide is that usually usually the kinetic term is just the first term that you wrote there is just phi dagger phi, but now you're adding this new term, which is sort of as 1 phi bar and 2 phis.
Yes, and
I
this
see. And
SY, it will generate SYK term when we go to onshore.
I see. And this is not like a superpotential term because that would be holomorphic. So this is some non-holomorphic cubic term that you have added.
Yes.
I see.
So this is a main difference between this model. Oh, Jim, do you want to say something?
You can write this as a holomorphic potential. Just take the d square that's at front and set it to only act on the phi bar because it annihilates the 2 factors of phi. And so if you write this as d bar square phi bar phi, that's indeed holographic.
A holomorphic. So
I'm sorry, holomorphic. Sorry. Yeah.
So okay, so this is just some superpotential that you have.
A superpotential, but that depends on the spinor derivative of the superfield. Normally, we don't do that superpotentials.
Okay, thanks.
Yeah, and I just want to add one more comment about the n equals 4 supersymmetric SYK model in literature. That one is actually the superpotential because that one is integrate over this chiral half of superspace, and then it is free chiral superfield. So you can also construct some kind of models like that too, and then you will get SYK type terms. Yeah, but this is because we want to construct more different models, and this is one of the models that we can construct. And then, and from this process of integrating all of this integrating out of the auxiliary fields, then we can get this term, which is nonlinear, but when you expand it, the first term will be the SYK term. Yeah, and then when we can look at this term, which at first sight may be a little bit complicated, but if you stare at it, we will have an analog of this coupling JIJKL. We call it JVCEF probably. And then you see this thing, because the kappa is chosen to be, is arbitrary, so we can choose it to be Gaussian random. Then you see one of the indexes here actually contracts with each other. And then these are complex conjugate of each other. So if we choose this to be Gaussian random, then this J will be Wishart-Laguerre random. So we get back something that occurs in like 1D n equals 1 and n equals 2 SYK models in literature. So this is indeed the SYK term. And after we check all of these, so after we check that we are not insane, we get the SYK type term, then we can just go from 4dn equals 1 to 1dn equals 4, the offshore version. Right. And a lot of calculations of correlators and stuff actually start from offshore Lagrangians. So that's why we provide this Lagrangian. And you will see these kinetic terms, and we also have 4 of these interaction terms, like offshore. So this is the first model that we construct, the simplest one. The second one, we can construct from Q-point superfield interactions. We can construct 4-point SYK models, which are on, like, by 4-point I mean like when you go onshore. So the first model from here, we also construct it entirely from chiral superfield. But now instead of 1 chiral and 2 anti-chiral superfields, you can do it 1 chiral and then like any number of anti-chiral superfields, and then you have a finite polynomial of these. And all of these kappas now are arbitrary. And when you go to onshore, then you'll see one of the term will look like this, which it also takes the SYK term form. So indeed, like this superfield Lagrangian will give us SYK terms too. And this is the offshore Lagrangian, which starts to look a bit lengthier and with more terms. The other thing that we can do is put some other multiplets in play. For example, we can just take this polynomial, and then instead of anti-chiral superfield, we just replace it by real linear superfield. Then we'll actually get the tensor supermultiplets, and we get like the only change from like for the SYK terms only is from these chiral fermions will become fermions from tensor supermultiplets. But of course, like when you are in offshore, all of these other terms are different. But if we just take out the SYK term and compare, the form is totally the same, but just its fermions are replaced by the ones from tensor supermultiplets. So the third method, so the second method, we construct 2 of these SYK-type vertices. And the third one is a little bit different. First of all, it is 2q-1 points when onshore. So it's the more general form of the SYK models. And then second, we use superpotentials to construct these. So let me have a little bit of recap. So like superpotentials are functions of chiral superfields only. And then when we integrate it over the chiral half of the superspace, is automatically supersymmetric, and with this plus HC. So first of all, we construct something we call Chiral Currents, which is done by pulling out the marijuana fermions from fractal of tensor supermultiplets, and then like contract them with chiral projection operators, and then see if they satisfy the chiral condition. And we see that for this, we call J11 is constructed from fractal supermultiplets. This combination is chiral. And we can also construct a thing called J22, which is, these are from tensor supermultiplets, and this combination is chiral. So we can, because these are chirals, then that means we can use that to construct superpotentials. And we consider superpotentials of this form, which is contracted by chiral superfield, like from the chiral supermultiplets, and also a polynomial of these chiral currents from either factor or tensor supermultiplets. So the first model we construct is from factor supermultiplets. So we have a kinetic term from chiral and a kinetic term from factor supermultiplets. And then we have like Q point interactions from one field from chiral supermultiplets and polynomial of this quadratic chiral currents in fermions from factor supermultiplets. And all of these couples now are arbitrary coefficients. So like when we do that, and when we go to components and go to onshore, then we will have a term that looks like this. So it will be it's also actually have a lot of terms, like you sum over I and j from 1 to p. So it's like some, like you have two polynomials and then you multiply them. But then if you want to get back the traditional form of that SYK term, which you only have the one term which is diagonal, then you can actually set all of it, because all of these couples are arbitrary. We can set all of them to 0 except one of them, so we can eliminate all the cross terms. And then this is the SYK type terms. And for tensor, what we do is just replace these arguments of this polynomial from the factor chiral current to the tensor chiral current. And the only difference is you replace the fermions by this fermions from tensor supermultiplets. So now we have constructed 5 models, and let me comment on the features of these models. The first comment is about the SYK type couplings and randomness of these models. Here I just put all the 4 points SYK models, and if you observe, all of them will take this form, which is with this coupling J, and this J is Wishart-Laguerre random, as I just described. And also it will have some kind of projection factors flowing around and with like 4 fermions. So, and then the other, so I want to mention one thing is this kappa ABC, this B and C is actually symmetric because we use bosonic superfields to construct these vertices. But the n=1 and n=2 models in literature, the CIJK thing is totally anti-symmetric. So how do we get back anti-symmetry is we treat this A and this B, the number of copies index and the spin index B as a pair of matrix, a pair of indexes. And then when we change the order of B and C, like as a pair, then because this one is anti-symmetric, it will give you back a minus sign. So overall, this is anti-symmetric. So that's why I mentioned earlier that we treat this as a pair of indexes that is analogous to the number of copy index in literature. And this is the first thing that I want to note. And the second thing is like why are these chiral projection factors like flying around is like, for example, in 1D n=2 models, the interaction term is like psi bar. And when we go to n=4, you can either like do it in like 4 component notation, or you can do it in like 2 component notation. So let's say this is a translation between 2 components and 4 components notation, like in for d n equals 1. So that means like d square will contain 1p plus and d bar square will contains 1p minus. So if you look at these index contractions, then if you throw the p plus here, then this will be side, and then throw this p minus here, this will be sidebar. So this is analogous to, so we get back this is analogous to it. And we can also look at the 2q minus 1 point SYK models, like with more fermionic terms. But now we set all of the kappas to 0 except one of them. So we eliminate all the cross terms and we only retain one diagonal term. And this again, if you look at the kappa, these two multiplied by each other, and these two are conjugates of each other, and only one index are contracted. So this can be written as an analog of the SYK coupling constant with like more fermions. And when these kappas are Gaussian random, this J will be Wishart-Laguerre random also. So this is how we look at our models and recognize them as SYK vertices. And the other comment that we want to give is about dynamical bosons. So in full Garatov meta sentence and such depth paper, at the very end of the conclusion, they talk about, because there are n equals 1 and n equals 2 models, ones with only fermions, and the bosons are auxiliary. They say they are wondering whether there are models with n bigger than 2, like for example n equals 4 supersymmetry, that would be this kind. So you only have dynamical fermions, but you don't have dynamical bosons. Yeah, but our response is so far in all of our models, we actually have dynamical bosons in it. The reason is simple reason is as follows. So if you just pull out like a simplest model with SYK interactions, like the 3 points that we have, these are chiral superfields, and then we just pull that out, and we find that the superspace integral is just like d squared d bar square, which contains like 2 time derivatives. And then, but you are talking about SYK type terms, so you will have 3 superfields. So you need to distribute that 2 among these 3. So there must be some kind of terms that you don't have derivative acting on it. So like even, for example, in free theory, you can do a trick of eliminating the dynamical boson by like just do some field with definition and then like force it to be auxiliary. But in this case, we cannot do that because of the existence of this kind of interactions. And yeah, so we have all the dynamical bosons in our models. But in fact, this is consistent. Like we are not insane because these models are consistent with the other like supersymmetric SYK models with same number of supersymmetries in literature. For example, the 1D equals 4 models in the earliest paper, they also contains dynamical bosons. And also, if you look at the 2D equals 2 models by Morgan, Stanford, and Witten, they also have dynamical bosons. So I think this is just a feature that we, at least for now, we would not be able to get rid of. So finally, I want to thank Jim and Yang-Wei for this wonderful collaboration of like for this paper, and also want to thank Anto, Jeff, Mark, and Anastasia for discussing and commenting on our paper. Want to thank Victor for organizing this seminar so that I have the opportunity to talk here, and I thank all of you for coming. Thank you.
Thanks, Hazel. There are more questions? I had a question myself, actually. So what is known about like IR behavior of this Lagrangians that you're writing? Do you like, maybe first question is, are they are interaction terms that you have relevant or irrelevant just by power counting? Oh,
So let's go to one of these. Um,
yeah, good. So what is the dimension? I mean, there should be some coupling constant, and is it what's the dimension of this coupling constant?
So just if we just do some kind of simple dimension analysis,
Mm-hmm.
this is 1 because we are in 1D, and this is 1, so the psi is 0.
Mm-hmm.
So so if you, so this is offshore, but if you, let's say, go onshore, and then you have 4 sides and then a J with 2 couples, and this will be 0, so that is 1, so that is relevant. So the fermionic interaction, at least, that is relevant.
Sorry, X, this bold X.
This is the auxiliary boson.
Yeah, but it has dimension plus 1/2, right? Okay.
Yes, this is plus 1/2. So this is 0. So this couple is plus 1/2. So when you go to
So
when
it's
you go on shell, so this plus 1/2 plus 1/2, this will be 1. But so it's positive and it's relevant.
it is relevant. So then it sounds like the theory will flow somewhere in the infrared, right? And
Yes.
is it? Do you have any idea where it flows? Like, what is is there some IR fixed point or I know approximate? I mean, in 0 plus 1, we usually don't get exact fixed points, but we get this approximate fixed, like original SYK, right? The non-supersymmetric SYK, it flows to the Schwarzschild zero, which is almost a fixed point. So there is some interesting long distance behavior. So I wonder if you have any conjectures about whether this Lagrangian flows in the infrared.
So first of all, we haven't actually calculated anything, like we haven't, so these are all guesses. So I cannot guarantee. And then so there's a paper by a bunch of people in Princeton, which is about n equals 4 JT gravity and stuff like that. So like JT gravity is written in super Russian, but what they claim is they find it very hard to find n equals 4 SYK models that flows to super Russian. But their arguments was about, so they start with a superfield that is fermionic and chiral, but they just write down the first 2 terms and hope that it will be like there will be no dynamical bosons. But what we show is if you write down a superfield that is starting, the lowest component is one fermion that you want, and the second component is some auxiliary bosons. Then when you write down this superfield, then you will find you need some kind of constraint that added to it, and then you will finally have dynamical bosons. So if you start from that assumption, yes, it's very difficult to find n equals 4 SYK from that assumption that will flow to super Russian. But what we, after our calculations, we think that is not a right starting point. Or like if you want to construct n equals 4 supersymmetric SYK models, then you will need to involve dynamical bosons, and you need to use bosonic superfields. So the arguments will be different. So we are not sure yet if these models can flow to super Gaussian, but at least the other models that they claim, those couldn't flow to super Gaussian. But we are different from them. So right. But this
I'm one of
obviously
the
need
co-
much more further calculations.
Oh, sorry, go ahead.
Yeah, we just yeah we
Luca
just need to do further verifications and calculations to see if that's possible.
Luca is here. He wants to.
Yeah, I'm one of the co-authors of the paper. And yeah, I guess what confuses me is that we give two possibilities there. And one is with dynamical bosons, and the boson being the lowest member of the supermultiplet, which I think is the situation you're in, right? The dynamical boson is the lowest.
Yeah, we have all that.
Yeah. So I guess our confusion was that we wanted it to, the model to flow to an IR fixed point that would be unitary. So we said that that would imply that the dimension of the dynamical boson in the IR should be greater than 0. Do you think that assumption is wrong?
Yeah, because like here, as you said, the dimension of this phi A is -1/2, right? So it's like a field of negative dimension, which is a little bit worrisome, but yeah. So how like can we be certain that this model is unitary? Maybe that's
in the IR, yeah.
Well, no, what do you mean in the IR? If the Lagrangian is unitary, the classical Lagrangian is unitary, I would say. Well, yeah, maybe that's a little bit of a worry. Like there is a field, this phi of negative dimension, and as you said, you have interactions, this cubic interaction that has it without a derivative, right? So it is a little bit like, yeah, one could worry if some zero mode of this field becomes a ghost, right? Roughly speaking.
Right. Yeah, I think our point was that there's no solution to the Swinger-Dyson equation that has dynamical bosons, so that we're in the situation that you're in, that has delta B greater than 0 and has B, sorry, the boson the lowest member of a supermultiplet. Do you think that's the wrong assumption? Because like we're saying that delta B should be greater than 0 in the IR, or maybe that's not the problem.
This I'm not sure, but I just want to mention if we start from a superfield with which is chiral and with the lowest component to be fermion, then it's actually unavoidable that you will have dynamical bosons. Yeah, because we are like quite some super like we are kind of like supersymmetric people. So this is the conclusion that we get. But I'm not sure about the thing like about like so you are saying like if you're saying like if these have to satisfy some kind of Swinger-Dyson equation set of like SYK.
Yeah,
then
so
it's not possible to have dynamical bosons, is that?
Yeah, that are unitary. Yeah. It's not possible to have bosons as the lowest component of a supermultiplet. So,
but
so it must be fermion.
There should be a less.
It could be fermion.
There should be a less fancy argument than Schwinger. Like if there's some problem with unitarity, like you should see it, in the UV fixed point without writing any. Without writing any Schwinger-Dyson. Well, not at the UV fixed point. I mean, you say, oh, these operators. The free theory is fine. The kinetic term is probably fine, right? And then, as you said, there is like a shift symmetry of phi that is important. Then there is this operator that breaks, at least naively breaks, shift symmetry of phi again. I mean, it's a complicated action. I don't, maybe it's total derivative the change or something. So maybe you can, maybe the Lagrangian shell, and then you can deform the gauge transformation and it survives. There could be all subtleties, right? But I think it's an interesting question. I mean, what you're saying is, to analyze, to make sure that there is no subtlety in this Lagrangian that somehow makes it non-unitary because of some zero mode. And then if it's not, then I think it's very interesting question to understand where it flows and what is like how because if this thing is unitary, it will flow to some unitary theory in the IR. Could be empty theory or could have some interesting IR behavior, right? I mean, that's another option that it just gaps out very fast. Maybe that will be not in conflict with what you're saying, right? Because you assume some approximate conformal invariance and what you're doing. So that could be another option. that it just gives us. Sure, yeah, we're sort of in a discussion mode, so let's see if you want to say something.
Sure. Thank you very much, Victor. Excuse me for not turning on my video, but
No
I got some issues here, and I don't want to scare all of you by showing you my face. But anyhow, this question is actually more. So let me say it this way. Hazel and Youngry and I that's actually one of the things we're most interested in, is whether it's possible to find a subtle loophole that will allow a system with n=4 supersymmetry and describe an SYK-type model to avoid having dynamical bosons. And in fact, the approach that we've used here starts with 4-dimensional supersymmetry, because we were also interested in knowing something about what SYK-type models lifted up to string theories, because if you can lift them, then you're in the realm of strings. So that's why we started at the other end. But there are a class of 1-dimensional n=4 systems which don't start from higher dimensions, and which we spent a long time studying, but we still found that they were subject to this same problem of dynamical bosons. We are not prepared to write a theorem to this effect, but we do know that it is very difficult to avoid dynamical bosons if you want n=4 supersymmetry and SYK-type couplings.
But do you also have a feeling that like dynamical bosons in 1 dimension are problematic generically?
Well, it depends on what you want to do with them. If you're talking about flowing to infrared points, the answer is yes. But again, there may be a loophole. As I said, we have lots more on this subject that we have not published. And that's one of the areas that we need to look very, very carefully to find out if there are loopholes somehow that we've missed.
But do you think a loophole, for instance, would be emergent supersymmetry in the IR?
Yes, I think that if we could find, remember, our starting point is that we always impose off-shell supersymmetry. Now, the point that I'm making here is that off-shell supersymmetry in high dimensions, when you take them to lower dimensions, they don't actually get all the supersymmetric models. That's why, for example, the heterotic string was discovered, right? I mean, it's a version, if you start in 4 dimensions, you'd never see the heterotic string. But if you start in 2 dimensions and take the heterogeneous structure of the Lorentz representations, and then you find heterotic strings. So it's that kind of loophole that I'm worried about for SYK, and I have no definitive way to argue that, that it happens.
Okay.
Could I ask one more question? I think
Sure.
I was wondering how can I see the fact that these Lagrangians have an SU2R symmetry? Where does that come from? 4 dimensions, or because in 4 dimensions there's no SU2R symmetry. So does it come from the dimensional reduction?
Yes, it would, absolutely. So the point is that you can take what we've done, and in particular, someone asked this question, Hazel said we use Majorana fermions because it's convenient for us. But if you reformulated everything we did directly in complex fermions in 4 dimensions and then do the reduction, then that means that you will automatically see, even in 4 dimensions, you'll see an SL2C symmetry, because that's just the Lorentz group acting on the fermions. But if you reduce to 1 dimensions, that should actually increase. And so, yes, we think we can see it that way.
So you're saying that SU2 is the compact, one of the compact subgroups of SL2C, so it appears under the dimensional.
Right, that's exactly what I'm saying. Yep.
And do you think that you guys can write a model? You mentioned that you can write models without starting from 4D. Do the models?
Yes, we can.
So this model has the feature that it has a U1 times SU2 symmetry, because the U1.
That's right. It's basically an R symmetry. That's exactly right.
So can you write a model in 1D that only has SU2 and doesn't have a U1 R symmetry? Doesn't have a U1, doesn't have the U1 factor?
In this class of models, I don't think so, but you notice that I'm hedging my bets.
Okay.
Okay.
Thank you very much.
Well, thank you guys for listening to Hazel's presentation.
Yeah.
She's one of my most wonderful students, let me tell you.
Yeah, it was a pleasure to meet you.
Yeah, thank you.
Yeah, we'll also put the doc online, and then if you want to refer somebody to it, then.
Great. Okay, I got to run now.
Okay, Hastu, thank you.
Thank you.
Bye-bye.